In this video, I'm going to show you how to use deep learning and create a convolutional neural network. So what I'm going to try here and do differently is I'm going to go really in depth about explaining everything. We are going to create our own data. We are going to create our own layers. And I'm going to explain each and every step of it, how every layer is made, why they are made like it. I'm also going to explain the maths and science behind it to create our convolutional neural network. And I'm also going to explain the basic topics to you, like what a convolutional neural network is, like why it's called like that, what are the layers that we can find in it. But I really want you to stay focused and watch the entire video, because in those 20 to 30 minutes, you will really get a deep understanding on how convolutional neural networks work. So let's get started. So first of all, as you can see, I have already created the network here using Matlab, and I'm using only the main packages that you have in Matlab. So what you will need to do is download Matlab and add the toolboxes that we are going to use. In this case, we are only going to use the Deep Learning Toolbox. So I'm not going to explain to you how to download Matlab. You can just go to the website. So you can download it for Windows, Mac, or any other operating system that they support. So let's see what we are actually going to build. So we are going to build a CNN. This is a convolutional neural network. So what is this? You've most probably seen a lot of documentation, a lot of information that those networks are used for classifying images. So what we are going to do here is we are going to classify images. So it makes sense to use a CNN, but how does it actually work? What does it do? So it uses a filter. So it applies a filter to an input that results in an activation. So what does this mean? So let's say we have an image here, which consists of bits. Like when we go down to it, it consists of bits, and there are certain characteristics around it. For example, I don't know, like you can spot something like this or something like this, and so on and so forth. So what a convolutional neural network is going to do, it is going to apply filters in order to find it. So it's going to try to find and map those characteristics. And this is going to have an activation function. So it is going to activate something. So let's see what layers we are going to need here. So we are going to need 8 layers, which is going to be our image input layer, our convolution 2D layer, batch normalization layer, ReLU layer, max pooling layer, fully connected layer, softmax layer, and classification layer. So let's go into each of those layers and see what they are actually good for. So the first one, the image input layer, tells the network the size of the images. So basically all it's going to do is tell the size of the images. So we are going to use images 32 by 32, which we are going to create later on. So Matlab has a lot of toolboxes. So in this case, we are using the Deep Learning Toolbox, which comes with a lot of functions, a lot of layers, a lot of characteristics. So we are not going to design the entire toolbox, which would be like ridiculous. It would take maybe a year to design from scratch, but we can use a lot of things already defined there. So all of those things define some mathematics and statistics behind it, which I'm also going to briefly explain on the way. So our next layer is our convolution 2D layer. So convolution is the process of highlighting expected features in an image. So what I have said here, we are highlighting certain features. So a convolution is a matrix multiplication operation. So there are different filters that can be used. For example, blurring filter, sharpening filter, horizontal Sobel filter for edge detection, and vertical Sobel filter for edge detection. So what I mean by that is that we have a matrix, and that matrix has some values, for example, 5, 2, 1, 3, 1, 0, 1, 9, 0, and so on and so forth. So we apply a mask to that. So let's say this is our mask, and our mask could look something like this. For example, 1, 1, 0, 1. So what we are trying to detect here by applying this mask to this matrix is seeing if we can find this characteristic anywhere. And if we find certain matchings, this means that we have found some type of feature, some type of characteristic in our code. So something like I have explained here. The next layer we have is our batch normalization layer, which is used for stabilization. Basically, it reduces the number of epochs. So we could also maybe get away without using this layer, but it's going to help us to make the algorithm run more efficiently. So the ReLU layer is a layer that uses the rectified linear unit activation function. So maybe this sounds like really out of the box now, but it is extremely simple. So it does the following. So it returns us x if x is greater or equal to 0, and it returns us 0 if x is less than 0. So what this means, it is extremely easy to compute. So what this means is when we have an input, if that input is greater or equal to 0, it will be equal just to that input. And if the input is less than 0, it will be equal to 0. So as I have already mentioned, it is really fast to compute. So it says that the neuron is only activated for positive values. So that's what you can take away from the ReLU layer. Our next layer is the max polling 2D layer. So the main thing that this does is it creates a layer that breaks the 2D input into rectangular polling regions and outputs the maximum value of that region. So again, we have a huge matrix here with values all over the place. So what this is going to do is it's going to break this 2D thing into like rectangles. We can specify if it should be like a rectangle or a square, or like we can specify the x and y on the rectangles, and it is going to calculate the maximum value for each of those. So what this is going to do is it's going to reduce the number of data points that we need to process. So you can imagine here, for example, we have 1, 2, 3, 4 data points, and now we have only 1. So in this super simple example that I have just drawn here, we went from 4 to 1. So it is going to reduce the number of data that we need to process. So as you can see, most of those layers, we can live without them. They are going to either make our algorithm faster, they are going to help us increase our accuracy, or in general, they are going to help us get the results we need. But we can experiment with this. We can try reducing some layers, removing them, adding new layers, and so on and so forth. Now we have our next layer, which is our fully connected layer. The fully connected layer contains all of the inputs to the outputs with weights and biases. So for example, so what we can do here is configure our number of inputs and outputs. So for example, what we could do is specify an output of 10. So we are going to have 10 outputting neurons for any number of inputs. So for example, let's say there are like 10,000 inputs or so, and we can specify it to 10. Or for example, if we need a classification problem and we want to classify between, I don't know, like a male or female face, what we can do is use the connected layer to have only two outputting layers from two outputting neurons from any number of inputting neurons. So you can see for what this can be useful. Now we have the softmax layer. The softmax finds a maximum of a set of values using the logistic function. So as I have explained here, we need to find the maximum in the max pooling 2D layer. So we need to find a maximum for each of those rectangles. And there are certain types for doing that. In this case, the softmax layer is going to use the logistics function. And the logistics function is going to be e to the power of q, k, so our input data at the point k. And here we have the sum of e to the power of qk. I'm really sorry for the bad drawing here, but you can just Google the logistics function. It really doesn't matter for us here, but it always helps to understand the math behind it. And then we have our classification layer, which is going to be our last layer. And the classification layer computes the cross entropy loss for multi-class classification problems. So what this means in simple terms is the difference between two probability distributions. So let me explain that. Let me first delete some of that stuff here. What this is going to do is, let's say we have our original value. So this is the truth, our original value. And then there is some distance between what we come up with, so what the model thinks. So this here is what our model thinks, so what we compute, what our neural network is going to think, and this is the truth. And this distance here between the origin and the model is the cross entropy. So I hope this helps you understand it a little bit more. There is also a lot of maths behind it that you can always look up. So how is this actually going to look in Matlab? So I have prepared the code here in advance because it would take too much time to type this out now, but I will post this to GitHub. And of course, if you're interested more, you can always head over to noveltechmedia.com and contact me there. If you would like to see more, or if you would like me to help you out with certain things. So those are our layers. So we have our image input layer, which is going to take our image. And here we are getting the images. I will explain that in more depth. Then we have our convolution 2D layer. We have our batch normalization layer, ReLU layer, max pooling, convolution batch. And again, so as you can see, we have this repeating 3 times here. So this is something that you can experiment with. In order to increase the accuracy, it is better to have more hidden layers or convolution layers, but it doesn't have to be. You could run into a problem of overfitting or underfitting, and this is exactly something that you should be experimenting with and obtaining different results. But I have used this version here since this brings us mostly to an accuracy of 98 to 100%. In some runs it's 100%, in some it's a little bit less, but it stays around there. So first of all, we want to find if an image is a circle or if an image is an ellipse. So what we are going to do is first we are going to generate those. And here I have created a generator file that is going to generate circles and ellipses. So of course, you could just download the images from the web. You can download 1000 images of ellipses and 1000 images of circles, and you could completely ignore the generate ellipses and create ellipses files. But what I have done here is I have created them manually, and you can just pull this code and create them manually. But there is just a lot of maths behind it, how to create it. For example, if you want to create a circle, let me delete this. You have to calculate certain angles. You have to calculate pi. You have to calculate the radius, and so on and so forth. So that's basically everything that is being done here. So calculating stuff like the cosinus, sinus, length, and so on. And here we generate the circle, and here we generate the ellipse from there. So to be completely honest, I have also copied a lot of code here for generating those files, since I really didn't want to go that deep into geometrics here. And one thing that we are doing here is we are returning, we are checking if an object is a circle or if it is an ellipse. So if it's a circle, it's going to be a 1. And if it is an ellipse, it's going to be a 0. And that's what we return here from our function. Now we are also 3D plotting this. And as you can see, this is going to just create a graph of the stuff we have created. And in the end, we also wanna save the images. And we are saving the images in the create ellipses files. So we cd into the folder ellipses. We traverse all the ellipses and circles we have created. And then we write them down and we save them. And we also save the type. The type is going to be a 0 or 1, depending if it's an ellipse or a circle. So basically, those are going to be just a bunch of images that are either a circle or an ellipse. And here we are also creating the name. Why I'm using this structure here in order to sort it correctly. Because if you sort it as 1, 2, 3, 4, when you convert this to binary, it is not going to be sorted like it should be. So we are using log 10 to change the number of zeros here. And we are having 1001, 1002, 1003, and 4, and so on and so forth. So we are going to have in the end 200, in this case 1000 ellipses and 1000 circles, and they are going to be sorted exactly like that. So the first 1000 is going to be ellipses and the second 1000 are going to be circles. Okay, so far so good. You can also look into the creation of the images here. So we are creating a frame, axis, we are grayscaling the images, so we want to have the images in a grayscaling format. So I'm not going to go really too deep into this because this is either Matlab specific or it just doesn't really have to do anything with neural networks and machine learning. It's just using Matlab to create images. So, but the interesting part here is in the ellipses neural net. So the first part here is, again, we cd into ellipses, we load it, we cd back, where we get the categories, we create this image data source here, we create a figure. So when I run this, you will also be able to see the figure. We traverse it and we title it. So what we want to do is title it either as a circle or as an ellipse, so that we have the truth of our data, so that we can know if something is a circle or ellipse. Those are our layers that we have specified. The next step is splitting the data into training and testing sets. So we can use the split each label function, which comes from the Deep Neural Network Toolbox. And we split it at a fraction where 80% of our data is going to be training and 20% of our data is going to be for testing. And we randomize it. The next part are going to be our training options. So by running train network, we are going to train our model, and this is going to return us a network. Later on, we can use this network to classify our labels. So again, we use the function classify in order to predict the labels and see if it is a circle or an ellipse. And here I'm just calculating the accuracy and test labels. So if I type the accuracy here, our accuracy in this run was 99%, sometimes it's 100. It depends on the run. But the interesting part are our training options here. So we have a lot of training options. So the first one here is the SGDM, which specifies the training method. So SGDM stands for stochastic gradient descent with momentum. So there is, again, a lot of maths behind it that you would need to check out, which would just be an overkill for this video. There are different ones like ADAM, which is for adaptive moment estimation, and RMSPROP, which is for root mean square propagation. So it really depends. Like, I'm just going to explain this very simply here. So what we need to do is we run the algorithm, right? And we constantly search for an optimum. So we want to find an optimum in here. And the main problem with this is the difference between global optimums and local optimums. So this is the global maximum. So this is the maximum value we can reach. And this is the global minimum. But when running our algorithms, the problem is that we could maybe be stuck here. Like, we could think that this is already the minimum, and we wouldn't continue, but we would find the minimum somewhere else. And the entire thing boils down to determining from case to case, from algorithm to algorithm, what makes more sense, because this is going to be really costly to find the global optimum and minimum. And it always comes down to trade-offs. And there is a lot of maths behind it, if you're interested. If you would also like to get more into this, head over to noveltechmedia.com or just email me, and I would be really glad to help you or point you in the right direction. So let's continue with our algorithm here. The next one is our initial learn rate, which is the initial speed of learning. Higher learn rates means faster learning, but the training may get stuck in a suboptimal point, which we have explained earlier. The mini batch size has to be smaller than our image size. Then we have epochs, which determines the number of epochs, the number of times this is going to run. It also depends on the number of data, so this is going to be multiplied with the number of data in each epoch. Then we shuffle our data. So we shuffle our data because it is going to generate better results. Every time we run it, we don't want to have the same flow of data. We want to randomize it in order to get better results. Validation data, we just specify our validation data here. Validation frequency. So with this, we can set the frequency, how often our data should be validated. Verbose false is going to give us some additional information like plotting and stuff, where we can see the progress. And plots, so this is what you can see right here. So the process here of learning is the plot specified here. And then the only part is just to train the network, predict the labels, and watch it happen. So when you get this code, first you need to run the create ellipses files by just clicking run, which is going to create all the images in here. And then the next step is just running this code here. So when you get this from GitHub, the only thing you need to do is create ellipses and then run this one here. So as you can see, for example, this is a circle, this is a circle, 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 ellipse, ellipse, ellipse. And as you can remember, ellipses are zeros and circles are ones. One more thing we could do is we have our predict labels. So what we can do is run predict labels, and for example 1, and this is going to be 1. So this is going to tell us that our first image is a circle. And as you can remember, the first 200 here are going to be all circles. So for example, 150 is going to be, okay, this was 250, sorry. Everything above 200 are going to be ellipses, because we have sorted them like that. So 201, 202, 203. And if we go back to 199, it's going to be a circle again. So let us run this again by just clicking run here. So as you can see, our algorithm is running now. This is our accuracy. It starts with 50 because like there is a chance of 50-50 between being a circle and an ellipse. And here is our loss. So the lower our loss gets with the increased accuracy, the better our algorithm is working. So this is where you can see like overfitting and underfitting. So if the validation data loss is greater than the training data loss, the neural network is overfitting data, and reversed, it's also like that. So overfitting like means that you are creating the model to work extremely well for a certain type of data, but it wouldn't work for a different type of data as well. And underfit, so this mostly comes because the neural network is too complex. And if the neural network is too simple, then you have a different problem. Then you have the underfitting problem, which results in like the accuracy being lower. But on the better side, it can accept a lot of different data. So let's run this now. So here we have finished our training and we are at 99.75% accuracy. So I would say that's pretty good for our little neural network here. And as I have already mentioned, in order to test this out, you can just use predict labels and check that image if it's a circle or an ellipse. So that would be it. I hope you learned a lot and I hope I could clarify stuff to you. If you want to learn more or are interested in working with me, you can head over to noveltechmedia.com and either book a consulting session with me or look at some courses over there, or generally just write me an email. You can find my email in the description down below, about what you would be interesting, about projects that you are maybe creating, and just give me your feedback. So I really hope you enjoyed this one. Thank you so much for watching and see you in the next video.